if we now look at all the rectangular regions within this strip from yi minus 1 to y sub I, of course we're talking about this strip here, we're talking about all the rectangles, then we have this segment that goes from x equals 0 to the square root of y sub I star, or something close to the square root. Well, from x equals 0 to the square root of y sub I star. The intersection of the plane, the xz plane, through this line is going to give us the graph of a function of a single variable. And we don't know what the function f of xy looks like, but maybe it looks something like this, and maybe it comes out here and does something like this. So right here, now we have a graph in 2 dimensions. Let me make that prominent and let the blue rectangle kind of fade into the background. So right there is a curve. That curve has an area that's represented by the integral of whatever function we get when we intersect f of xy with the plane y equals y sub I star. The volume of the region of the graph corresponding to this strip again being this strip, is going to have, well, the approximate volume above this strip is going to be equal to the area of this graph, which we can get by integrating f of x y sub I star, times the width of the interval, which is your delta y sub I. So we got a distance here, delta y sub I, and we got an area here. Now I can actually kind of depict that region. It's probably going to get pretty messed up, but let me try to do it anyway. I've got a better picture on the next board. And I've got too much purple in this to really see the shading, but it's got to look something like this. And here's a better picture. Hopefully a better picture. I think it's a better picture, maybe you don't. And you're entitled to your opinion, that's fine. Again, we had our red and green rectangle down here. We had our altitude here, which comes up to the graph of this function. Right there is the point x sub j star y sub I star f of x sub j star y sub I star. But now we've got the whole graph and the whole strip of the region underneath the graph. Now this is only an approximation. We don't know what slope there might be in the y direction, and we haven't accommodated that. If that's bothering you, it should. But there's kind of a picture. The volume, again, of this strip is delta xj times delta y sub I times f of xj star y sub I star. And the delta xj should have a star on it. The delta y sub I should have a star on it. Okay, well, the total volume then of our entire rectangular approximation for the entire region in the xy plane, the entire region that we started with here, is going to be what I've written here. Okay, what have I got here? I've got the area of a typical rectangle. Okay, the area corresponding to a typical rectangle. The area above a typical rectangle in this strip or in any other strip. I sum those areas from j equals 1 to m. J is the index for x, which means that I move from all x, I move through all x values from one end of the strip to the other, okay, according to our x partition. So that what I have here is a sum of all the volumes of all the little rectangular solids in this strip. So I have a good approximation to the volume between this value of y and this value of y. The volume above this strip here in our original figure. Okay. Then what do I do? Well, I sum all of those up from I equals 1 to n. Well, I equals 1 to n takes all the y strips, y's evaluated from y, partition from y0 to yn, y sub I being the typical interval, typical index in the partition. So I'm summing up all the volumes of all the rectangles in all the strips. Okay, here's all the rectangles in one specific strip. I sum it over all strips. I get the volume of all the rectangles. All the rectangular solids. I'm telling you rectangles. It's rectangular solids. So there's the sum. That's a J. Okay, well, now I want to look at the circled expression here. The sum from j equals 1 to m of xi star y j star xj star yi star. That is a j, but let's make a better hook on it. Okay. Now, there's that sum. What's that sum mean? Well, as your xj's approach 0, this does approach an integral of the continuous function f of x y sub I star with respect to x. And the sum goes from j equals 1 to m. Okay, well, xj's end at x sub m, which is equal to the square root of y sub I. So the sum goes to the square root of y sub I. The sum takes x values then from 0 to the square root of y sub I star. Now, f of x y sub I star is a function. It's the function we got when we sliced the surface by the plane y equals y sub I star. This curve right here. We extended that curve on both sides for a distance delta y sub I and got a volume. Okay, we're not interested in what happened to the delta y sub I, but what we have when we integrate this function is the area of the curve that we got, the first curve that we got, between 0 and y sub j star. If we multiply that area, well, by the width, then we're multiplying the area of this face by the width, and that's going to give us the volume of the curve. So this is the volume of this is the volume above the jth strip. Now, if we multiply this, I'm sorry, just thinking where to put this. If we multiply this times by delta y sub j, we get the area of that strip. Okay, so that means the volume of this corresponding strip becomes this times delta y sub I. Now we sum that from I equals 1 to n, and we get the volume above all the strips. You can kind of visualize what that might look like. I'm not going to even attempt to draw it. Okay, here's the volume of the ith strip, or above the ith strip. if we take this summation and shrink our delta y sub i's down to 0, our n will of course approach infinity, we're going to get this integral. Okay, our y sub I stars are going to become y's, our delta y sub i's are going to become dy's, and we get this integral. And then we illustrate how to evaluate this integral for a typical function f of xy equals xy. Now the evaluation is very easy. We have the integral from 0 to 2 of the integral from 0 to square root of y of f of xy dx dy. Okay, inner integral f of xy dx from these limits, outer integral from 0 to 2 with respect to y. So, replacing f of xy with xy, we perform the integral. Okay, treating y as a constant, we integrate with respect to x. We get x y squared over 2, and it's evaluated between 0 and the square root of y. Well, plugging in square root of y for x, we get the square root of y squared, and of course plugging in 0, we get 0, so we don't bother writing it. And this just becomes y squared over 2, and now we integrate y squared over 2 from 0 to 2, and we get 2/3, and that's going to be the area of the region.